Now, in the last few sections, we have learned the nitty-gritties of molecular dynamics simulation. So, let me summarize it very quickly. We started with understanding of the force calculations that we have to do in the trajectory, and we understood that we have to understand that we are solving the second order differential equation. There are some very important assumptions like Born-Oppenheimer. With that understanding, we also looked at that we can do finite difference models in order to calculate the trajectory of the atoms, and that is where we looked at time trajectory, and we understood that the time step, which is what the focus of this section was, is very important parameter, because that is essentially decides what kind of errors you are going to look at. So, when you look at Taylor series expansion, if you do Verlet algorithm, which is very efficient, quick algorithm, but may not be as accurate, then you can look at the various ideas like velocity Verlet or Beeman algorithm to increase the accuracy of the system. But most often that we are looking here and using, which is called fifth order predictor corrector gear algorithm, because that is quite stable as well as quite accurate algorithm, because we are using the 5 term Taylor series expansion, and we are looking at the expansion up to the 5th, or what we should say 6th element in the Taylor series, starting with x 0, and then we are going to the first differential, second differential, third, fourth and fifth differential, and by calculating all these differential, we are able to calculate the trajectory of particle. So, if it is at initial position x 0 at time t, then t plus delta t, this is the next position of the particle, can be then calculated using fifth order predictor corrector algorithm, and we looked at that how we set it up. But important factor there was that the time step is related with the vibrational frequency of the atomic systems. So, if you look at a diatomic molecules like argon or krypton, xenon, you know that what is the vibrational frequency of that leads to what we call as the wavelength. Now, your time step should be smaller than the wavelength time, primarily because you are trying to create that trajectory within that wavelength time. So, frequency of oscillation of the atomic systems becomes an important factor, and then because these systems are working at 10 to the power minus 10 meters, which is angstrom size. So, and if you look at the frequency of vibration, your time step goes into 10 to the power minus 15 of the second, which is called femtoseconds. So, if you have to go to 1 microsecond, you have to go up to million time steps. And again, when you take this million time step, you are not going to integrate in every time step, but every 5 time step to 10 time step, 15 time step. What I mean by 5 time step is that after every 5 time step, we are going to recalculate the properties. So, we are looking at that point the force, we are looking at that point kinetic energy, potential energy, the summation of that. We are also looking at maybe temperature at that instantaneous temperature, instantaneous pressure, etc. is a snapshot at those levels. But depending on how many time steps we take in order to do the calculation on the time trajectory, we are then doing averaging over time. And so, the statistics depends on the size of this particular time trajectory. So, the time step becomes very important issue, as well as the position. So, a bit about position, we can start with a randomized position, but then we do not know where the atoms are. Atom may be right on top of each other from 12-6 potential, you know, it could be very strong repulsion. So, we want to start with a known trajectory, known positions of the atoms, and the best way to get the known position of the atoms is their solid phase and their lattice structure. And if you look at phase centered cubic is the important structure for the argon crystals, and so we start with that. So, we know that they are at very equilibrium status, we know their position, distances, etc. We can make sure that potential energy is minimum at that location, equilibrated. So, that equilibration is another point, and because we are doing this calculation on all pair of atom I j, then comes the important factor that for this pair potential calculation, are we going to calculate over all atoms? So, if I look at 108 atom system, then I have to take atom 1 and do 107 calculations, because there are 107 other particles. And if I take them in the pairs of the 2, still I am left with at least 2 at a time. If we take, then there are 1/2 of those particles are there, which we have to calculate. So, if you look at this kind of situation, even if we look at the idea that I j, force of I j is equal to minus of J I. So, there is a third law of Newton, equal and opposite reaction. So, if I calculate I j, I do not have to calculate force, which is J I, still I have large number of atoms. So, we come up with a smart technique, which is cutoff radius. We know that potential function can go to 0. We cut it off, because as it moves out, we have shifted that force potential to go to 0, so that we do not have to go to infinite tail of the attractive part of the Lennard-Jones potential. So, with that understanding 2.5 sigma, we use that cutoff radius to also create the neighbor list. So, now we go to that 2.5 sigma and do the neighbor list and understand what are the atoms around, what are moving in, moving out, keeping that track of neighbor list. Now, we have reduced our calculation quite a bit. So, anything outside cutoff does not matter. So, the time step, the positioning, the neighbor list, and then comes the periodic boundary condition. And we looked at in molecular dynamics simulation that reflected boundary versus periodic boundaries makes a lot of difference, because the reflected boundary is confining the system, and it is around, there is no other forces. As soon as you make periodic boundary condition, then the atom can move out, and another atom shows up with the same velocity vector, conserving the force and energy. With that understanding, we are now creating no artificial surfaces. So, it simulates the bulk properties, and because we already know the bulk properties of material, this becomes very important boundary condition, because if we want to compare with the bulk temperature, bulk specific heat, bulk modulus, elastic constant of the bulk material, we have to use periodic boundary conditions, because now in the bulk situation we are not creating any artificial boundaries. So, with the understanding of 5th order predictor corrector algorithm and the concepts of cutoff radius, shifted force potential, periodic boundary condition, and neighbor list, now we are ready to write a computer program. As you know, in computer program there are lots of languages which are called higher level languages. For the structured programming, you talk about C, C++, Fortran, Java, J2EE, Enterprise Edition, whole bunch of programming languages are there. You can also do it in Python and other scripting languages which are coming up, or even use some packages which are out there like MATLAB, Maple, or other mathematical packages that are out there used in order to calculate the trajectory and solving the second order ordinary differential equation. I have taken my codes that I have worked with earlier, written in Fortran 90 and 2000. Primarily, Fortran is still the language for computation which is highly optimized and used by all kinds of parallel processing and supercomputing engines. And if you look at in molecular dynamics world, Fortran is still a language of choice, and it has become quite a well known model to use. So, I am going to use Fortran as a programming language, and then take you through various parts of the molecular dynamics program. So, let us now get ready for writing and understanding a molecular dynamics program. Thank you.